Safe navigation in dynamic unknown environments still faces many challenges, mostly due to deficiency in robot perception, mobility, and various uncertainties. Obstacle avoidance is a key component of safety, which often involves temporary patrolling of the obstacle border. To find the best complete path, global planners build a comprehensive model of the scene. They typically suffer by data incompleteness, errors, and are computationally expensive. Computational effort is reduced in local planners, which reduce the planning horizon to the current vicinity of the robot. However, most of them assume either zero or slowly changing and unknown obstacle velocity up to now. The extreme case is a reactive controller that merely maps current observation into control. In this area, only fully actuated robots were mostly studied. The obstacles were rigid with simplest shape. Their overall velocity and posture were accessible, and the rigorous justification of local convergence were rarely provided. This research deals with reactive, safe navigation in presence of unknown obstacles that are not even rigid. Unlike overwhelming bugs of previous works, they are a continuum of arbitrary and time-varying shape that may move and deform in any way, rotate, ring, screw, wiggle, etc. Examples include reconfigurable obstacle, forbidden zone between dynamic obstacles, virtual obstacles like contaminated area, or online estimate zone of the operation of a hostile agent. We consider a realistic non-hologramic under-actuated constant-speed vehicle with a lower limited turning radius, exemplified by wheeled robots, aerial and underwater vehicles, and many other systems. There is an unknown moving and deforming obstacle. Only the distance to it and the time derivative of the reading are accessible by robots. Border patrolling mission consists of advancement on the obstacle and subsequently following its border at a given distance d0. An example is escorting a convoy of vehicles. Border patrolling is used for vehicle guidance to a steady target in a scene cluttered with many moving and deforming obstacles, where a given safety margin should always be respected. The bearing of the target is measured. The distance to the obstacle is available only within a given sensing range. This switching navigation law is offered to patrol the border. It employs a linear function with saturation chi. Its slope gamma and the saturation threshold delta are tunable parameters. The use of this law relies on the expectation that the motion will mainly be over the sliding surface. The differentiate d plus chi of d minus d naught equal to 0, whose equation does drive the distance d to the required value d naught. However, this property needs justification and proper controller tuning. These are concerned by main theoretical results of the paper. We first disclose conditions necessary for a robot with a given speed and minimum turning radius to be able to patrol the border of the obstacle. In doing so, we do not pre-specify a control law and utilize concepts from the continuum mechanics to characterize the obstacle. Then we prove that under slightly and partly unavoidable enhancement of the necessary conditions, the proposed control law has full ability to cope with the problem and provide relevant recommendation on controller tuning. This controller is used by the proposed strategy of safe navigation to the target in the face of many moving and deforming obstacles. The strategy offers to flip between border patrolling and moves to the target in a straight line. A straight move is replaced by border patrol when the distance to the nearest obstacle reduced to a critical value. The converse switch holds when the requested distance d0 of the border patrolling is nearly reached and the obstacle is headed towards the target. Performance of the proposed law was tested via simulation and real-world experiment. For brevity, I will discuss only navigation to the target. Here, the robot has to bypass a large cross rotating about moving pivot as shown in Figure A. The robot first moves straight to a target until the distance to the cross reduced to a trigger level in Figure B, and then turns left and avoids the obstacle in Figure C. Finally, the cross is bypassed and the robot arrives at target in Figure D. The real-life experiment was carried out with a wheeled Pioneer 3DX robot. This particular experiment involved both static and moving reconfigurable obstacles. The path of the robot is shown in Figure D. In this work, a sliding mode method for unicycle-like vehicle navigation has been elaborated for the problem of border patrolling and collision avoidance in the case of moving and deforming obstacles. Its efficiency has been illustrated by computer simulation and experiments with real robots. That's the end of my presentation. Thank you for your attention.